Welcome to week 11, Recurrent Neural Networks, RNNs, and Sequence Modeling. This week, first, we will look at Introduction to Sequence Modeling and RNNs. Day 2 will show us understanding RNN architecture and backpropagation through time, which is BPTT. Day 3 will be covering long short-term memory or LSTM networks. Day 4 will look at gated recurrent units, which are GRUs. Day 5, we will be looking at text preprocessing and word embeddings for RNNs. Day 6, we'll do sequence to sequence models and applications. And finally, for day 7, our RNN project will be on sentiment analysis. So let's get started with week 11. Welcome back to week 11. This week we will start our day 1 with the introduction to sequence modeling and RNNs. Now let's go over the overview of sequence modeling. What is sequence modeling? Sequence modeling involves predicting or generating outputs based on sequential data. Unlike standard models, which assume independence between inputs, sequence models capture temporal or contextual dependencies. Why is sequence modeling important? First, NLP, natural language processing. Tasks like language modeling, machine translation, and sentiment analysis depend on understanding sequential relationships in the text. Time series analysis. Sequence models are essential for tasks like stock price prediction, weather forecasting, and sensor data analysis. Next, let's go over the introduction to recurrent neural networks or RNNs. What are RNNs? RNNs are specialized neural networks for sequence modeling. They include recurrent connections that allow them to maintain a memory of previous inputs. The structure of RNN has input layer, which processes sequential data one step at a time. Then it has a hidden state, which maintains information about past inputs. And it has recurrent connections, where we pass hidden states from one time step to the next. Let's look at the key concepts in RNNs. First, we have hidden states. These represent memory at each time step. Recurrent connections enable information sharing across time steps. Vanishing gradient problem. Challenges in training long sequences due to diminishing gradients. Let's look at some of the key applications of RNNs in machine learning. We have text generation, which generates new text based on learned patterns. We have language translation, which converts text from one language to another. Stock price prediction, which predicts future stock prices using historic data. Another application is speech recognition, which understands spoken words and phrases. We have video frame prediction, which anticipates future frames in video sequences. With all this in mind, let's jump into hands-on exercise, where our objective today is to pre-process a text dataset for use in RNNs and set up an environment in TensorFlow and PyTorch for building RNNs. I know I mentioned or here, TensorFlow or PyTorch, but we're going to look at both the options today. So let's jump in. First, I'm going to go over TensorFlow. So I'm going to start a new file, Python, save it as day1 underscore, I'll call it TensorFlow. Let's start with some of the libraries that we need. So I'm going to go ahead and say from TensorFlow, TensorFlow dot keras dot datasets import IMDb. Since this is the first day of the week, I'm going to go ahead and explain each line. You can just forward this if you don't like it, but I'll probably go over each and every line. So this line imports the IMDb dataset, a standard dataset for sentiment analysis, where each review is represented as a sequence of integers, and that's our dataset that we're going to use. Next, from TensorFlow dot keras dot preprocessing, I am dot sequence. I am going to import pad underscore sequences. Now this imports the pad sequences function used to ensure all sequences which are reviews are of the same length by padding or truncating them. Okay, so that takes care of it. Just make sure that there's no typos, because that comes back and bites us later on. Next, I'm going to go import TensorFlow as TF. This will import the TensorFlow for deep learning operations. Now next, I'm going to say from TensorFlow dot keras dot models, I am going to import sequential. Now we have used this before. This imports the sequential class used for building a sequential, which is layer by layer model. Next, I'm going to say from TensorFlow dot keras dot layers, I am going to import embedding, and I'm going to import another one, simple RNN, and I'm going to import dense. So these import specific layers. Embedding converts word indices to dense vectors. Simple RNN implements a basic RNN layer, and dense is fully connected layer for output. So let's go ahead, and now next I'm going to set up some hyperparameters. Let's say vocab size equal to 10,000. This is the vocabulary size that I want. The top 10,000 most frequent words will be used here. Next, I have max underscore length equal to 200. This is the maximum sequence length. Reviews will be truncated or padded to 200 words. So every review is 200 words. Next, I'm going to go ahead and load the data using the IMDb dot load underscore data function, and I'll say number of words that I want here will be equal to vocab underscore size. I don't want the entire thing, but just 10,000 words, which I'm defined in line number 7. Now this will give us x underscore train, y underscore train, comma, x underscore test, comma, y underscore test. So this will give us the training and testing data for us. Next, so again, just loads the IMDb data set. Number of words, as I mentioned, restricts the data set to the top 10,000 words, most common words, and then x train, y train, x test, y test, these lists of integers representing word indices, and binary label 0 for negative and 1 for positive for the y items. So next, let's go ahead and pre-process the data. So I am going to say xtrain equal to pad underscore sequences, as I mentioned earlier. I'm going to use that function for, anyway, first I'm going to type this max length equal to max underscore length, and padding equal to, I'll set it as post. Here what I'm doing is I'm ensuring that all the reviews have the same length, which is max length of 200, and then the pad sequences with zeros at the end, which that's why I mentioned post. So padding happens at the end, and truncates reviews longer than 200 words if it's more than 200 words. So that's what this does. Now I'm going to do the same thing for our test data set. So here, test max length, perfect. So this is good. Now next thing I'm going to do is print the data set just to check it out. So I'm going to say print f of training data shape, and for that I'll specify x underscore train dot shape, and then for my test data shape, keep a space here, x underscore test dot shape. Perfect. So I have that. I'm going to move all the way to the top. So this kind of prints the shape of the padded data set for confirmation. So you can run this application. I can go here and say Python day 1 TensorFlow or dat1 underscore TensorFlow. This will get the data and show me my 25,000 by 200, 25,000 by 200. So that's what I have. So perfect. So I have my training and test data set available. Now next, I am going to build the model. Now to build the model, I'm going to say model equal to sequential, and here I will pass embedding, which is with input dimension of equal to vocab underscore size and output underscore dim equal to 128. Here what I'm doing is first I'm using sequential, which is a model built for stacking layers sequentially, and in with embedding I'm setting input dim equal to vocab size, where input vocabulary size is 10,000 words, and output dim equal to 128, where each word index is mapped to a 128 dimensional vector. Next I'm going to use simple RNN, and to this I'm going to pass 128 comma activation equal to, I'll use tan h this time, and I will say return underscore sequence equal to false. So what I'm doing here is I am creating a initializing simple RNN, where I'm giving the number of RNN units to be used is 128. I'm saying activation function for the RNN is tan h, and I am saying that this outputs only the last time steps results. That's why I say return sequence equal to false. Next I'm going to create a dense layer, where I'm going to say 1 comma activation equal to sigmoid, and then finally I'm creating a fully connected output layer using dense. The one is the outputs a single value for binary classification, and then finally we have the activation equal to sigmoid, which ensures the output is between 0 and 1 probability. So perfect. So that kind of created my model. Now next let's go ahead and compile this model. So to compile it, I'm going to call the compile function model.compile, and I'm going to pass the optimizer equal to, use same what we used before, Adam. I'm going to say loss equal to binary underscore cross entropy, since we are looking at binary data, and metrics that I'm interested is, as usual, accuracy. So here we are compiling with optimizer Adam, which is optimizer for training. Loss binary cross entropy is loss function for binary classification, and metrics accuracy evaluates the model's accuracy during the training process. So now once I'm done with this, I can just say model dot summary. This displays a summary of the model architecture, including layers, parameters, and output shapes. So now let's go ahead and train this model. To train this model, I'm going to create a history variable, and I'll say model dot fit and pass it x underscore train. I'll pass y underscore train. Number of epochs that I want to run it for is 5. I'm going to keep it small so it doesn't take much time. Batch size equal to 32, and I'm going to say validation split equal to, so this is how much validation split I want to give. I want to give a 0.2, so 20-80% split. So again, x train, y train is the training data and labels. Then we gave trains for 5 iterations over data set, that's why epochs is 5. Batch size 32 processes 32 samples at a time, and validation split is 0.2, uses 20% of the training data for validation. So next let's go ahead and evaluate the model. So I'm going to say loss comma accuracy equal to model dot evaluate evaluate, and to that I'll pass x underscore test and y underscore test, which I've done before. This tests the model on the unseen test data set. Outputs for this will be loss, which is the final loss on the test set, and accuracy will be accuracy on the test set. Now finally let's go ahead and print this off, these things. So f test loss is loss colon 0.4 f, and next I'll also display test accuracy, which is accuracy 0.4 f. Perfect. So I'm gonna go ahead and run this. I'll clear this out and run this again. Okay, there's probably some typo or something that I missed, so I'm gonna go ahead and check here. Looks like it's on return sequence false, where I have mentioned instead of return sequences, return sequence, and that's why it's giving me an error saying unrecognized keyword. So I'm going to save that, clear it out, run again. And now it's going to give me the model summary, and it's going to run for 5 epochs. So while it is running, let's go ahead and start our process to code in the similar thing in PyTorch. So I'm going to go ahead, create another file, save it as day1 underscore pytorch.py. For this, first I'll import torch, import torch nn dot nn as nn. Next I need to import torch dot optim as optim. Next I want to from torch dot utils dot data I will import data loader and tensor dataset. So what I'm doing here is first the core PyTorch library for tensor operations, which is torch. I'm importing that. Torch.nn, that is the module for building neural networks. We have torch.optim, which is optimizers for training neural networks. And finally, torch.utils.data. These are utilities for working with dataset, which includes data loader for batching and tensor dataset for packaging data. So once I have that, next things that I need is from TensorFlow dot keras dot datasets. I am going to import IMDb. That's the dataset. That's why I'm using TensorFlow right now. TensorFlow dot keras dot pre-processing dot sequence import pad underscore sequences. So these we have just used, which impose the IMDb dataset and the pad sequences function from TensorFlow for pre-processing. Next, let's go ahead and build some hyperparameters, same as last time. I'm going to say vocab size equal to 10,000. And then I'll say max underscore length equal to 200. So this is again same as vocabulary size is 10,000 and maximum sequence length is 200. The vocab size, what I'm trying to do is I'm trying to get only the top 10,000 most frequent words are used, and max length is each review is padded or truncated to 200 words. Next, I am going to go ahead and load and pre-process the data. I'm going to use same thing that we did before, xtrain, comma y train, and then x test and y test. I am going to say IMDb dot load underscore data, load data, number of words equal to vocab underscore size. So this again loads the IMDb dataset, and each review is a sequence of integers representing word indices, and ytrain and ytest contains the binary sentiment labels of 0 and 1. Next, pad the sequences. So that is x underscore train equal to pad underscore sequences, and I'll give x train comma max length equal to max length, and padding, I want to pad at the end of the, if it's not enough, I'm going to say not enough data in there, I'm going to add padding of zeros at the end. Same thing I'll do for x underscore test. Do the same thing here. Perfect. So that takes care of that. So that's again pads or truncates reviews to have a fixed length of 200 using the pad sequences. Now let's go ahead and prepare the data for PyTorch. So till now whatever we did was same as earlier code, but now I'm going to say train data set equal to tensor dataset torch dot tensor x underscore train torch dot tensor y underscore train. So this line converts NumPy arrays into PyTorch tensors and creates a data set of paired inputs and labels. Same thing for train, or not same thing, train loader equal to data loader To this, I'll pass the train data set, and I'll say batch size equal to 32 and shuffle equal to true. So what this does right now here is it batches the data set into groups of 32 and shuffles the data for training, which means our next step is to define the RNN model. So I'm going to say class RNN model, use the nn.module as input. Now first is our initializer method, so I'm going to say init underscore, pass it self, comma, vocab size that I want to use. Next I'm going to say embedding underscore dim. I want to use hidden underscore dim. I will use output underscore dim here. Then call the super method RNN model, pass RNN model and self to it, and call the initializer function. Perfect. Next, self dot embedding equal to nn dot embedding, and then pass the vocab size to it and embedding dim to it. Next, for self dot rnn, I will pass nn dot rnn and pass it embedding dim, hidden dim. It needs whatever I mentioned during the slides. It needs hidden dim and batch first equal to true. And then finally, I'll say self dot fc equal to nn dot linear hidden dim and output dim. So here what this init function does is it defines the model architecture. nn.embedding embeds the input word indices into dense vectors. Then nn.rn is a simple recurrent neural network layer, and nn.linear is a fully connected layer mapping the RNN outputs to the final binary sentiment prediction. Next, let's create the forward function. def forward self and x. Now in here I am going to say embedded equal to self dot embedding of x. Next, for output and hidden, I will use self dot rnn and pass it embedded, and then I'll return torch dot sigmoid self dot fc of hidden dot squeeze of 0. So here what I'm doing in the forward function is I embed the input sequences, passes the embedded sequences through the RNN, hidden contains the RNN's last hidden state, and finally applies the fully connected layer to the hidden state and uses the sigmoid activation to output the probabilities. So that's what we're doing here. Now once I'm done with this, I'm going to go ahead and initialize the model by calling that class that I've created, RNN model, and pass it. We'll have to pass the vocab size, which we already have set to 10,000, but I'm going to specify here. I'm going to say embedding dim equal to 128. I'm going to say next one is hidden dim equal to 128. Next, I have the output dim to provide, and I'll say output dim that I'm expecting is of 1. So here what I'm saying is I'm initializing the RNN model with the specified parameters, with vocabulary size is 10,000, embedding dimension is 128, hidden dimension is 128, and output dimension finally is 1 for binary classification. So it will be 0 or 1. Now let's go ahead. Our next step here is to define the loss and optimizers. For that, I'm going to use criterion variable equal to nn dot bce loss is what I'm going to call. This is the binary cross entropy loss function. Next, I'm going to call optimizer equal to optim dot, I'll use Adam as usual, and I'll say model dot parameters is the first parameter that it needs. Next, I'll say learning rate equal to 0.001. So again, what I'm doing here is criterion is what computes the binary cross entropy loss for the predictions, and optimizer optimizes the model using Adam with a learning rate of 0.001. Next step here is to train the model. So I'm going to create a function called as train RNN, and this will take inputs as model train underscore loader. I think I've created that, but I don't see it. Train underscore loader. Next, I'll use criterion. Next, I'll use optimizer. And finally, I'll say epochs equal to 5 by default. So if you're not specified, and I want to keep it minimum, just like a TensorFlow. Talking of TensorFlow, let's look at the results over there. So it went through the 5 epochs. It gave me the test accuracy, test loss here. 85% is the test loss. Accuracy is 53%. So there you go. That's how it shows. Now let's compare this with PyTorch that we have. Should be almost same. First, I'll start the training process by calling model.train. And now for each epoch in range of epochs, depending on how many epochs we pass, if not, it's 5. Epoch loss, I'll create a variable where I'll set it to 0 initially. And then I'm going to go from batch by batch, take X batch and Y batch in train underscore loader. And then for each of them, first I'll use the optimizer dot 0 underscore grad, so 0 out the gradients for the optimizer. Then I'm going to say predictions that I am looking for equal to model of X underscore batch dot squeeze, so it can properly fit in to 1 of loss equal to criterion. And then to this I'll pass the predictions and Y underscore batch dot float if it's not in float value, loss dot backward, so that's first. And then I'll have to optimizer dot step it up, and I'll now do epoch underscore loss plus equal to loss dot item, as we have done before. So this model.train sets the model to the training mode here, and then for each epoch we initialize the cumulative loss initially to 0. For each batch in the train loader, I am saying optimizer 0 grad, which clears the previous gradients that has been calculated. Then we get predictions, which makes the predictions here. Then loss equal to criterion, it calculates the loss. I am computing the gradients here. And then this one optimizer.step updates the model weights, and I am adding the add batch loss to epoch loss here and keep on incrementing. And finally, let's go ahead and print for each epoch. I'll say epoch plus 1 comma loss is epoch underscore loss slash divide by length of train loader and 0.4f. So that will print me the epoch loss. I'm going to save this. Next thing is I'm going to call the training function. I'm going to go outside and say train underscore RNN, and I'll pass it the model. I have the model. I have the train loader. I'll pass the train loader. Next, I can pass the criterion. I have that. And next, it needs optimizer. Now, if you want to pass epoch, you can pass epochs, but I'll leave it because I'll use 5. So this will train the RNN for 5 epochs using the training data. Finally, once it's trained, let's go and create the evaluation loop. Evaluate underscore RNN. To this, I'll pass model X underscore test and Y underscore test. Inside this, I'll say model dot eval. So this will set the model to evaluation mode. Now next, with torch dot no underscore grad. So this disables a gradient computation for efficiency, and I am going to say predictions equal to model and pass it torch dot tensor x underscore test dot squeeze of 1. So this will give us predictions. Now for loss, I will say criterion, and to that I'll pass the predictions, and it needs the torch converted into tensor of y underscore test dot float. Perfect. So that will give me my loss. And now finally for accuracy, I will say predictions. If predictions is greater than 0.5 is equal to torch dot tensor at the particular location y underscore test dot float cos dot float. Then so this will give me the float value. Then I can just go ahead and get the mean of this particular item, so this will give me the accuracy for that. Now finally, let's go ahead and print our f test loss is, what is our test loss dot item, and I'll say 0.4 f. Now for test accuracy, I will say accuracy 0.4 f. So this will give me the loss and accuracy printed out. So that kind of finishes our entire loop. Now the only thing left is to call evaluate RNN and pass the model, pass x underscore test, our data set xy underscore test. So I pass that. This will finally evaluate the model on the test data set and print the loss and accuracy for us. So this is saying something is wrong. Maybe I did not predications. Okay, whatever it is, just make sure that you follow along. I hope there's no other typos. These are the TensorFlow warnings, so that's fine. They're already there. I'm gonna go ahead, clear, or no, not clear it out, but I'm gonna say, actually, let me clear it out. I'm gonna say Python day1 underscore pytorch.py. Let's hope there is no errors. There is pad sequences. Where is that? So in my pad sequences of x train, max length of max length, and my max length is here. Max length looks like the parameter is not max underscore length but max length. Again, you can check here, max length equal to max length. Yeah, perfect. I used underscore. That's not right, so I fixed that, clear it, and run it again. And it, as you can see, it's running for epoch 1, so it's going to take some time. So we'll come back to it once it gets over. So as you can see, it ran through the 5 epochs and then gave me the epochs and loss. I think I pressed something here, that's why it gave me this thing here. But it went through 5 of the epochs and gave me the loss. And you can see the test loss is 0.67 and this test accuracy is 0.56. So this is how you can pre-process a text data set using for use in RNNs and set up an environment in both, as we saw, TensorFlow and then PyTorch for building RNNs. I hope you were able to follow along. And just to summarize, we understood the importance of sequence modeling in NLP and time series analysis. We learned the structure and functioning of recurrent neural networks. We gained hands-on experience setting up environments and preparing datasets for RNNs. And we finally built a foundational knowledge for advanced sequence modeling tasks. If you had any issues while implementing this, saw some errors, or have any questions, do let me know in my messages and I'll get back to you. Day 2. Understanding the RNN architecture and backpropagation through time, which is BPTT. So first, we're going to look at detailed architecture of RNN. The different components of RNN include first the input layer, which takes sequential data, example words, characters, or time series values as input at each time step. Hidden layer, which maintains a memory of the past inputs through recurrent connections, the hidden state at time t of ht is calculated as h of t equal to f of wh times h of t minus 1 plus wx times xt plus bh, where wh is the weight matrix for recurrent connections, we have wx, which is the weight matrix for input connections, bh is the bias term, and f is the non-linear activation function. X can be a tan h or ReLU. For the output layer, it produces output yt based on the hidden state of ht, which is yt equal to g of wy times ht plus by, where g is the activation function, can be softmax for classification. Now next, let's talk about backpropagation through time, which is BPTT. Now what is BPTT? BPTT is an extension of standard backpropagation to handle sequential data in RNNs. It calculates gradients for each time step and propagates them backward through the sequence. Steps for BPTT include unroll the RNN across the sequence for a fixed number of time steps, then compute the loss for each time step, then backpropagate the errors across all time steps to update the weights. Challenges in BPTT include: first is vanishing gradient problem. Gradients diminish exponentially as they are propagated back through time. This leads to difficulty in learning long-term dependencies. Then we have exploding gradient problem, where gradients grow exponentially, causing numerical instability during the training process. What are the solutions? First, use gradient clipping to handle the exploding gradients problem. Then, use architecture like long short-term memory LSTM or gated recurrent units GRU to mitigate the vanishing gradient problems. And we'll look at both of these solutions later in this week. Next, let's talk about limitations of the vanilla RNNs. First is the short-term memory struggle to learn dependencies in long sequences due to the vanishing gradients. Second is the sequential computation. It cannot parallelize training across time steps, making them computationally expensive. And third is the sensitive initialization. The performance depends heavily on proper weight initialization and learning rates. With all this in mind, let's look at our today's hands-on exercise, which is much similar to yesterday's, where we will be building a simple RNN model for text classification using TensorFlow and or PyTorch. We're going to use both, and then train the RNN and observe how it captures sequence patterns. We'll be using our dataset as IMDb movie reviews dataset for sentiment analysis. That's what we did in the yesterday's video too. I'm not going to go into complete details of each and every line, but I'm going to go just roughly over what I'm doing. You can follow along and code with me for this particular exercise. So again, I'm going to start with a new file, Python file, save it as day2 underscore. First, I'm going to implement TensorFlow, so I'm going to call it TensorFlow. In here, first, I'm going to import the necessary libraries. So I'm going to say from TensorFlow dot keras dot datasets, I will import IMDb. Next, from TensorFlow dot keras dot pre-processing dot sequence, I will import pad underscore sequences. Next, I will import TensorFlow as TF. Next, I will import from TensorFlow dot keras dot models, I will import sequential. Next, from TensorFlow dot keras dot layers, I will import my layering tools, which is embedding, simple RNN, and dense. Perfect. So I have all my imports in place. Next step that we did was loading the data set. So I will say first vocab size equal to 10,000. This is the vocabulary size that I want, and then I want the max length equal to 200. Next, I'm gonna get the data set into x underscore train, comma y underscore train, x underscore test, comma y underscore test equal to imdb dot load underscore data, and I am going to specify number of words that I want to load from here equal to vocab underscore size. So this will pick the top 10,000 words from there. Next, I will pad the sequences to ensure uniform length. For that, I'll say xtrain equal to pad sequences, pass it our xtrain, and max len equal to max underscore length, padding equal to post padding. So I'm going to make sure that everything, if it's not 200, it will pad at the end. X underscore test pad sequences to x test, where I'll say max length equal to max underscore length, and again padding equal to post padding. Next, I have to print these shapes of training and test data set. So I'm going to say print of f training data shape is x underscore train dot shape, not function. Next, I will say the testing or test data shape equal to x underscore test dot shape. Next, I will go ahead and build and train the RNN model. Now first I'll define the RNN model. So I'm going to say model equal to sequential, and inside sequential I'll pass first embedding, and this needs input dimensions equal to vocab size. Next, I'm going to say output dimension, output dim equal to 128. Next, I will create a layer with simple RNN where the input will be 128 in this case, activation equal to ReLU, I want to use tan-h, and then I'll say return underscore sequences. Last time I did this error, but this time nope, false. And then finally the output layer, dense 1 activation equal to sigmoid for our binary classification. So perfect. So now next I'll compile the model. I'll say model dot compile. To this I'll pass the optimizer as Adam, loss equal to binary underscore cross entropy, and metrics equal to accuracy. So we have our compiled model here. So let's go ahead and print how it looks like. At this point I'll say model dot summary, so we'll see the model, and once we have that I can go ahead and train the model. I'll create a parameter variable history and say model dot fit, and inside this pass the x train, we need y train, we need epochs equal to 5. I need the batch size of how much to take once, and I'll be using 32, and then I'll say validation split equal to 0.2. So 20% of the data is for validation. Next, I am going to get I'm going to create this loss and accuracy. That will come from model dot evaluate method, and I'll pass x underscore test and y underscore test to it to get the accuracy. So now to print the accuracy, I can say print f test loss is loss 0.4 f, and test accuracy equal to accuracy, and this is again 0.4 f. So this will display my loss and accuracy. Now that I have this, let's go ahead and say, let's say I'm in the right place. Okay, Python day 2 underscore py TensorFlow. I'll run it, and while it's running, I can also run create the PyTorch example. So it's running through our epochs. So I'll go ahead, create a new file, save it as day 2 underscore PyTorch. Okay, I'll have to rename this. So now that I've renamed it as .py, I'm going to go ahead and first say import torch. So these are my necessary libraries. Let's go through one of them, each one of them. Import torch nn.nn as nn. Next, I need import torch.optimizer optim as optim. Next, I need from torch.utils.data. I need to import our data loader, and I need the tensor data set. Perfect. Now I have that. I'll go ahead from TensorFlow dot keras dot datasets. I need to import the IMDb database. Once I have that, next is again from TensorFlow dot keras dot preprocessing dot sequence. Preprocessing dot sequence. I will import our pad sequences. Okay, so once that is done, I can first load the data. I can use the same code that I used here. Go here, vocab 10,000, max length 200, xtrain, xtest, ytest, IMDb load, and pass the vocab size here. Next, I want to do the pad sequences, which is same as this. And do this pad sequences. Once that is done, next I need to prepare the data loader. Now is actual for PyTorch, where I can say train data set equal to tensor data set. This will convert from TensorFlow to PyTorch. I'm going to say tensor x underscore train. So that's done for x train. Next, I'll need torch dot tensor for y underscore train. So that looks good. Next thing that I want to do is get the train loader, or training loader, which is coming from data loader. And to this, I'll give the train data set. I'll set what batch size I want of 32, and I'll say shuffle equal to true. I want the data to be shuffled. So I have that thing ready. Now next, we'll have to go ahead and define the RNN model. So I'm going to say class RNN model nn.module. I pass that as the parameter. I'll create my initializer function, pass itself. It needs vocab size. I need embedding. Did I spell it wrong? Embedding. Okay, there you go. Dim. Next, I need the hidden dimension. Next, I need output underscore dimensions, and I think that's all that's all my initializer needs. So now first step is to call the super with RNN model and self and initialize it. Perfect. So once that is initialized, I can now use the embedding equal to nn dot embedding, pass it the vocab size, and it needs the embedding dimensions. So I have that. I'll pass the embedding dim. Okay, self, not slef. Next, we need self.rnn equal to nn.rnn, capital RNN. In this case, I need the RNN needs first embedding dimension, then it needs the hidden dimension, and then it needs the batch first equal to true parameter. Next, I'm going to say self.fc. For this, I need nn.linear, and linear will have hidden dimensions, and it needs output dimensions. That's about it. So that's my initializer function. Next, we write the forward function, which needs myself and x. And for first, I'm going to say embedded equal to self dot embedding with the value of x. Perfect. Next, for output and hidden, I will say self dot rnn and pass it the embedded. And finally, we return torch dot sigmoid and pass it self dot fc of hidden layer, and then we'll squeeze it. Squeeze with 0 as a parameter. Perfect. So that's forward is done. Now that is done, let's go ahead and initialize the model. To do that, I'm going to say model equal to RNN model, and to this we'll pass first is vocab size of 10,000. Next we have the embedding dim, which is 128. We'll say hidden dim equal to 128, and then we give the output dim of 1. So these parameters is what we pass to create our model. Now let's go and define the loss and the optimizers. For that, say criterion equal to nn dot, and we have used nn dot bce loss, which is the binary cross entropy. Next, I'm going to set the optimizer equal to optim dot adam and pass it the parameters of the model. So parameters. Next, I'll say the learning rate equal to 0.001. Perfect. So that takes care of our loss and optimizer. Now let's go ahead and write the function to train the model. So to that, train RNN, it needs model, it needs train loader, it needs criterion, optimizer, and our final epochs equal to 5. Let's set the default to 5. Now that is done, let's put the model in training mode by calling the train function, and then write our for loop to go through each and every epoch in the range of epochs. And for each of them, let's go ahead and first initialize our epoch loss equal to 0. And then let's go over each and every for x underscore batch, comma, y underscore batch. These are my batches of images and labels. So I'm going to say train loader. I will say initially optimizer dot zero out the gradient from the previous ones for every single optimizer. Next, I'm going to say predictions equal to model with x underscore batch and squeeze with 1. Next, I will calculate the loss equal to criterion and then pass it predictions, comma, y of batch dot float value. Convert that into float. Next, I will have loss dot backward. Next, I'll do optimizer dot step 1. Okay, so that's steps. Next, finally, I'll say epoch loss. Let's increment that based on the current values item. So that will increment that. So that kind of takes care of everything. And I'm going to say print which epoch is it. Epoch plus 1 because it starts from 0. Loss and epoch loss divide by length of I think it's train loader. There you go. So divide by that, and that's my 0.4f data to display. So that will display my loss at the end of every single epoch. Next I want to do is let's go ahead and call the training function. So to do that, I'm going to just say train RNN, pass it our model. We have our train loader available. We have the criterion available. we have our optimizer available. The only thing we don't have is epochs, which will use the default 5. Now that is done, let's go ahead and evaluate, right? The evaluate loop. I'm going to say evaluate RNN. It needs 3 items: model, X test, and Y test. And in here, first we'll put the model in evaluation mode. Next, open the torch dot no grad. So make sure there is no gradients, and then let's start with predictions equal to model and pass it torch dot tensor. Convert the X test into tensor, to torch, so it can understand, and then squeeze it with a parameter of 1. Perfect. I think I closed it at the wrong place. Okay, that's good. Next, let's calculate the loss equal to criterion and pass it predictions and torch dot tensor. So tensor that we have in y underscore test format dot so convert into float to float. Perfect. So that's that. Now we need to calculate the accuracy. For accuracy, I will say uh, predictions. If predictions is greater than 0, then let's make sure using the same parameter greater than 0, then torch dot tensor of y underscore test dot float and of the entire float, and then I will have to get a mean of that for the end item of that mean. Perfect. So I have my accuracy. Once I have accuracy, let's go ahead and print this out. F of test loss is loss dot item and display it in 0.4f. Next, I want to get the test accuracy, which is accuracy in 0.4f. Perfect. So I've displayed both loss and accuracy. Now the only thing that is left is evaluate RNN, pass the model, pass the x underscore test, and pass y underscore test, and it'll do the rest for you. So perfect. So while this is been, we were coding that, it ran our TensorFlow model. Now I'm going to run the PyTorch one. Say Python day2 underscore PyTorch. 68 and 58 for TensorFlow. Let's wait for a little while, let it run, and then we can compare both of them. And there you go, it ran. And if you see the comparison between TensorFlow and PyTorch, it's a little bit different. If you see, the loss is 68 and this is 67. Accuracy is 58%, this is 50%. So probably I'll use TensorFlow in this particular case. But again, depending on how many epochs you use, it might get better and better over time. So play around with different options and see how it all works. Just to summarize, today we gained a deep understanding of RNN architecture, including the hidden states and recurrent connections. We learned the concept and challenges of backpropagation through time, which is BPTT. We understood the limitations of vanilla RNNs and why they struggle with long sequences. And we developed hands-on skills in implementing RNNs in TensorFlow and PyTorch for sequence-based tasks. So if you have any questions or had any problems while following along or implementing this, let me know in the messages and I'll get back to you. Day 3. Long Short-Term Memory or LSTM networks. Today, let's start with introduction to LSTMs and how they address RNN limitations. Now first, what are LSTMs? Long Short-Term Memory LSTM networks are a type of recurrent neural networks RNN specifically designed to handle long-term dependencies. LSTMs mitigate the vanishing gradient problem by using specialized gates to manage the flow of information. Some of the key features of LSTMs include memory cells, which maintains a long-term memory state across sequences. It has gated mechanisms, which regulates how much information to keep update, or forget at each time step. Effective for long sequences. It handles sequential data with dependencies across many time steps. Now, what are the advantages of LSTM over vanilla RNNs? First, it retains long term dependencies. Next, it prevents gradient related issues during training. And it outperforms RNNs on tasks like language modeling, speech recognition, and time series forecasting. Now, let's look at LSTM's cell structure, which is input, forget, and the output gates that it has. First, for the forget gate, it decides what information to discard from the cell state. Its formula is defined as Ft equal to sigma of Wf dot of Ht minus 1 comma Ht plus B of f, where Wf is the weight matrix for the forget gate, Ft is the forget gate output, Xt is the input, and Ht minus 1 is the previous hidden state. Now let's look at the input gate. This decides what new information to add to the cell state. And the formula for this is It equal to sigma of Wi times Ht minus 1 comma H of t plus Bi, where sigma is the sigmoid activation function, Wi is the weight matrix for the input gate, and Ht minus 1 is the hidden state for the previous time step. Xt is the current input. Bi is the bias for the input gate. Next, let's look at cell state update. This combines the forget gate and the input gate results to update the cell state. And the formula is C of t equal to f of t dot of ct minus 1 plus I of t dot c of t dash. Now next, let's look at the output gate, which decides what information to output at each time step. The formula for this is Ot equal to sigma of W of O times H of t minus 1 comma x of t plus Bo, where Wo is the weight matrix for the output gate, Bo is the bias for the output gate. That's it. So I hope you understood these formulas and what they are used for. And let's go ahead and look at applications of LSTMs. First is the natural language processing, NLP. Here we can use it for sentiment analysis, machine translation, and text generation. Next is for time series forecasting. It can be used for predicting stock prices, weather patterns, or sales trends. And in speech recognition, it can be used for converting spoken words into text. It can be used for anomaly detection, where you can use for identifying unusual patterns in sequential data. With all this in mind, let's jump into our hands-on exercise for today, where the objective is to build an LSTM model for sentiment analysis on the IMDb movie reviews dataset and compare its performance with a basic RNN model. I'm just going to use TensorFlow today. You can try this out in PyTorch too. And if you had any issues in PyTorch, let me know. And I'm going to go ahead and start with the TensorFlow project. So first, let's create a new file. I'll save it as day3 underscore exercise.py. Here, first step is to import the necessary libraries. So I'm going to go ahead and import TensorFlow dot keras dot datasets, and I will import from there IMDb. Next, from TensorFlow dot keras dot preprocessing dot sequence, I will import sequential. Next, I will import TensorFlow as TF. Next, from TensorFlow dot keras dot models, I will import sequential. Wait 1 second. From sequence, I want to import pad sequences. Here is where sequential is from models. Next, from TensorFlow dot keras dot layers, I will import embedding. Next, simple RNN. I'll also get LSTM this time and dense. So there you go. So we have that. Now let's go ahead and load the data set. So for that, I will first set my vocab underscore size equal to 10,000. If you remember from last, this is the vocabulary size that we want. Max length for each input should be 200. If not, we pad it, or if it is, we'll cut it short. X underscore train, comma Y underscore train, comma X underscore test, Y underscore test. I will say IMDB dot load underscore data, and the number of words that I want in this case is vocab underscore size. Perfect. So that will load my data. Next, I'm going to pad the sequences to ensure uniform length among all the sequences. For that, if you remember from last 2 days, xtrain equal to pad underscore sequences. I'll pass it xtrain. I'll pass it max length of max underscore len, and I'll say padding equal to post padding. So at the end of it, add padding. If not, if it has enough value, just trim it. Next, xtest equal to sequences, xtest, max length, padding, post. Perfect. Next, I'm going to go ahead and print the shapes of the training and test set. So for that, I'm going to say print f training data shape x underscore train dot shape. Now same thing for, I'll do test data shape equal to test shape. So this will display those. Perfect. Now that we have this, next step will be to build and train the basic RNN model. For that, I'm going to start with RNN underscore model equal to sequential, and in here I will set the values with starting with embedding, and I'll pass input underscore dim equal to vocab underscore size, our output underscore dim equal to 128 with this layer. Our next layer, I'm going to say simple RNN, give it the input 128, activation equal to tan of h, and then return underscore sequences equal to false. Next, our final output layer, dense with 1, activation equal to sigmoid. So there you go, our model, RNN model is ready. Our next step is to compile the RNN model. So I'm going to say RNN dot model, or sorry, RNN underscore model dot compile. Optimizer I want to use in this case, same as what we always use, Adam. I'm going to say loss equal to, since it's binary data, binary underscore cross entropy, and metrics I'm interested is accuracy. So that's done. Next, let's go ahead and let's run the model. I'm going to say RNN model, or display the model summary. So I have my model code here. Perfect. Next step is to get the train the model actually. So let's go ahead, RNN history equal to RNN, RNN underscore our model dot, let's fit the data, x train, y train, we need epochs equal to 5. I will have a batch size of 32, and finally I need to say the validation split underscore split equal to 0.2. So these are all my parameters for my model to run. Next, I'm going to go ahead and evaluate the model. That will give me RNN loss, comma RNN accuracy. For that, I'm going to say RNN underscore model dot evaluate and I'll pass x underscore test, y underscore test. So that's evaluated. Let's go ahead and print our f of RNN test loss is RNN underscore loss 0.4f test of test accuracy of RNN is RNN underscore accuracy 0.4f. So now we just have created our model and evaluated the model after training. So next step is to build and train the LSTM model. So LSTM underscore model equal to sequential, and this will take, first I'm going to take copy from above because most of it is same. So we need embedding input dim equal to vocab size and output dim equal to 128. Instead of this, I'm going to say LSTM now. 128 activation is 10h, return sequences false, tense 1. As I mentioned, LSTM is nothing but an advanced RNN. So that's why it's pretty much almost same. Next, I am going to go ahead and compile. I'm going to do the same things. So I'm going to just go ahead and copy this entire stuff here. So first is to compile. So this time I'm going to say LSTM model dot compile Adam binary cross entropy metrics equal to accuracy. Then next step is LSTM model summary. Next I'm going to do instead of RNN history, I'm going to say LSTM history, and this time I'll run the LSTM model fit xtrain ytrain epochs equal to 5, batch size 32, validation split is 0.2. Next I am going to go ahead LSTM loss and LSTM accuracy is equal to LSTM model dot evaluate x test and y test, and then finally let's display LSTM test loss is LSTM loss and accuracy is LSTM accuracy of 0.4f. Now if I want to print them separately, the test accuracy, I can do that too, but we can just look through here and then compare the test accuracy of RNN and LSTM together. So I'm going to go ahead and open my terminal and say Python, project name is day3 exercise.py, and I'll give it some time. I'll come back to this in a couple of minutes to see how it does after all the 5 epochs for both RNN and LSTM. So it took around 10 to 15 minutes or so, I guess, because when you're staring at it, running through the different iterations, it's kind of painful. But here you go, we have our sequence, the model RNN, and then we have our LSTM model here. And these are the RNN test loss is 66 and 58, whereas this one loss is 34 and accuracy is 85. If you see, much better as compared to RNN, LSTM is based on the data that we have provided. So in this case, I will be using LSTM for sure. So I hope you are able to get this working. If not, let me know what happened. If you had any issues or problems, let me know and I'll get back to you. And just to summarize, today we went and understood the architecture of LSTMs, including input, forget, and output gates. We learned how LSTMs address limitations of vanilla RNNs. We gained hands-on experience building LSTM for sentiment analysis, and we compared LSTM performance with RNN and interpreted the results. So if you had any questions, if you had any issues, let me know and I'll get back to you. Day 4, gated recurrent units or GRUs. Let's go over introduction to gated recurrent units, GRUs. Now what are GRUs first? Gated recurrent units or GRUs are a simplified variant of long short-term memory LSTM networks. GRUs are designed to retain long-term dependencies while reducing computational complexity by having fewer parameters. Some of the key features of GRU include simpler architecture. GRUs have 2 gates, update and reset, compared to LSTM's 3 gates, input, forget, and output. Efficiency. Fewer parameters make GRU computationally faster and less prone to overfitting on smaller datasets, and it retains performance comparable to LSTMs in terms of capturing sequential dependencies. Now let's talk about GRU's cell structure, update, and reset gates. First, let's talk about update gate. It determines how much of the previous hidden state to retain and how much to update with the new information. Reset gate controls how much of the past information to forget when combining with new input. Hidden state update. It combines the new information and the past hidden state based on the reset and update gates. Now, when to use GRUs versus LSTMs? Now, depending on the feature, for example, if you have gates, for LSTM you use input, forget, and output. For GRUs, we have update and reset. As compared to parameters, LSTM has more parameters and GRU has fewer parameters. As per performance, it's better for complex longer sequences, and its GRU is comparable for shorter sequences. For training speed, slower due to complexity, whereas GRU is faster due to simpler structure. Use cases for LSTM include NLP and speech recognition. For GRU, it's time series data and small data sets. Now let's talk about our hands-on exercise. Today our objective is to build a GRU-based model for the IMDb movies review dataset and compare its performance with the LSTM model. What we are going to do is we're going to pick the same exercise from yesterday where we did comparison with RNN and LSTM. Now we're going to add one more to it, which is LSTM model. So let me pick that up. So I'm going to go here. I am going to create a new file, Python file, save it as day4_ex4.py, and I'm going to also open yesterday's file, which is our day3 file, which is day3ex. Copy this code from yesterday, paste it here. So this one now has both RNN and LSTM. Now our next step here will be, so we have these two. I'm going to just copy paste this here. Also, we might need some libraries above. So we have here IMDb, we have the pad sequences, TF sequential, we have embedding, simple RNN, LSTM. The only thing that is missing is GRU. So I'm going to add that GRU here. Next, I think rest of the stuff stays exactly same, but here at the bottom where we just copy pasted this code, I'm going to say GRU sequential, embedding input dimensional this thing, output dimension 128. Here I'll say GRU of 128, activation tanh, return sequence false, dense 1, everything else remains same. Again, now this is GRU model. So I'm going to say GRU model dot compile optimizer Adam loss binary and cross entropy and metrics equal to accuracy. For my GRU history, I'm going to use my GRU model dot fit, and inside this I will use xtrain, ytrain, epochs 5, batch size 32, and validation split is 0.2. Next, I'm going to get my GRU loss and GRU accuracy, and then get my GRU model dot evaluate xtest ytest and print GRU test loss, say GRU loss and GRU accuracy. So perfect, GRU test loss and test accuracy for GRU. I'm displaying it here. Now we can go ahead and compare all of them together by running them. So I have all three. Perfect. Now let's open terminal and let's make sure I'm in the right folder. Yes, I am. And I'm going to say Python day exercise 4, run it. And now, since it's running through 3 different models, I'm going to give it some time and come back to this video after around 15-20 minutes, maybe more, because RNN will run faster, LSTM takes longer time, and GRU is much more faster, as you can see. So I am going to stop here and come back in some time. It took around 20-30 minutes. I don't know. I stopped count after a particular time, and when I came back, I saw that it was all run. This is our RNN, which has 67% loss and 59% accuracy. Our LSTM has 38% loss and 86% accuracy, which we've seen already, and it's much better than LSTM. Now let's compare GRU to it. Our GRU is a loss of 46%, which is higher than LSTM in this particular case because the data set is much bigger, and 86% accuracy versus 86% accuracy. So accuracy is slight better in LSTM, but it's very close. Maybe if we run for more epochs, we can see much better improvement in either of these. So try to play with it and let me know how it goes. And just to summarize, today we understood the structure and functionality of GRUs, including update and reset gates. We learned when to choose GRUs over LSTMs for sequence modeling tasks. We gained hands-on experience building GRU-based models for NLP tasks. And finally, we compared GRU performance with LSTM models to identify the trade-offs. If you had any issues while following along and building this application or have any questions, let me know in messages and I'll get back to you. Day 5. Today, let's start looking at importance of text pre-processing. Now first, what is text pre-processing? Text pre-processing involves cleaning and preparing raw text data to make it suitable for machine learning models. It is a critical step for achieving high performance in natural language processing tasks. Some of the key steps involve tokenization, which splits the text into individual units. Example, it can be words or sentences. Here is an example where I love NLP is kind of split into I, love, and NLP, three different words. Next is stemming. It reduces words to their root form by removing suffixes. For example, running or runner becomes run. Then we have lemmatization, which converts words to their base form using a vocabulary. For example, better becomes good. Now, why is pre-processing important? First, it reduces noise in the data. Second, it standardizes the input for models. And third, it improves feature extraction and model accuracy. Now, let's talk about introduction to word embeddings. Now, what are word embeddings? Word embeddings are dense vector representations of words that capture semantic meaning. Unlike one-hot encoding, embeddings represent words in a continuous vector space. Some of the popular word embedding models include, we have word2vec. The models are continuous bag of words or CBO and skipgram. It captures word relationship based on context. Then we have glove, which is global vectors for word representation. This uses word co-occurrence statistics to generate embeddings, and it represents global semantic relationship. We'll be using this in today's exercise. Next, we have pre-trained embeddings in frameworks. Frameworks like TensorFlow and PyTorch offer pre-trained embeddings for quick integration. Let's look at some of the benefits of word embeddings. One, it reduces dimensionality, it captures semantic similarity, and it improves the model generalization. Now let's look at using some of the pre-trained embeddings for NLP tasks. Now, why use pre-trained embeddings? One, it saves computational resources. Second, it leverages large, well-trained models. And third, it boosts the performance for downstream tasks. Some of the popular pre-trained embeddings involve glove, which is pre-trained on datasets like Wikipedia and Common Crawl, and as I mentioned, we're going to use that today. Fast text handles out of vocabulary or OOV words through subword embeddings. And then we have embedding layers in deep learning frameworks like TensorFlow and PyTorch. Now, with this, let's jump into our hands-on exercise where the objective is to pre-process a text dataset and integrate word embeddings, example glove, into an LSTM model for sentiment analysis. So let's get started. First, I'm going to create a new file, Python file, save it as day 5 underscore ex dot py. Now you'll see one file already in there. Let's talk about that file before we do that. So for glove embeddings, you can go to this website nlpstanford.edu projects glove, or just search for glove and this should show up. In here you'll probably say download pre-trained word vectors, and there will be a zip file right here which you can download. Now once you download this glove.6b.zip file, what you're going to get is, I'm going to show my downloads folder. It will give you this glove.6b zip file. Inside that you'll have a bunch of different embeddings, 300D, 200D, 100D, 6p, and this is pretty huge. It's around 800 some MB. So once you have that, take the 100D and put it in your folder. In my day 5 folder, I put that file over there which has all the word embeddings in here. So that's what we'll be using. So next step, I'm going to go to the file and first import the necessary libraries. I'm going to say TensorFlow dot keras dot datasets. Again, I'm going to use the same dataset from before, which is IMDb. Next, from TensorFlow dot keras dot preprocessing dot text, I am going to import tokenizer. Next, from TensorFlow dot keras dot preprocessing dot sequence, I will get pad underscore sequences. So these are 3 things that I need right now. Let's go ahead and load the data set. So I'm going to say load data set. First one, I'm going to say, first I'll say vocab underscore size equal to same as what we used before, 10,000. Next we are going to set the max length to 200. Was it 100 or 200? I'll set 200. Next I'm going to say x underscore train comma y underscore train and x underscore test comma y underscore test equal to imdb dot load underscore data, number of words that we need equal to vocab size. So once I have that, next step is to decode reviews to text for pre-processing, which is what we're going to do is I'm going to say word underscore index equal to imdb dot get underscore word underscore index. So I get word index. Next I'm going to say reverse the word index variable equal to, I'm going to say value is key for key value in word index whatever I've created above dot items. So this will give me the reverse word index. Next I'm going to get my decoded reviews equal to, I'm going to create a string concatenation where I'll say join and I will say reverse underscore word index dot get I minus 3 comma question mark for I in review in x underscore train up till 5. I am missing in review for review in x underscore train. I don't need this, and I think I have extra closed, or let me try again. So I said reverse word index dot get I minus 3 for I in review for review in, oh I forgot to close this one, in review for review in x train colon. Okay, perfect. So that looks perfect to me. So that will give me my decoded reviews. Next step is to pad the sequences. So I'm going to say pad sequences. Now here I'm going to first do pad x train equal to pad sequences, pass it x train. We've done this bunch of times. Max len equal to max underscore length, and then we give padding at the end. So I say padding equal to post. Same thing I'm going to do for x test padding, pad sequences, x test, max length, post. Perfect. So that takes care of it. Now let's look at the shapes. Print f of training data shape is equal to x dot underscore train dot shape, comma, y underscore train dot shape. Perfect. Now next I will do it for test data shape, which is x test and y test dot shape. Perfect. So this, it completes our first step where we load and pre-process the data set. Our next step is to load the pre-trained glove embeddings. Now this is new, so we're gonna go through this very carefully. First, for this we need numpy, so I'm gonna go ahead and import numpy as np. Next, we're gonna load the glove, just say glove embeddings, even though the official way to write it is with capital V. Next, I'm going to say embeddings underscore index equal to empty, and then I'll get the glove file that is in my same directory as this, and the name of the file is glove.6b.100d.txt file. If you want to cross check, you can just cross check here, 6b100d txt. Perfect. So that's the path. Now next I'm going to say with open glove file in read format. I don't have to write anything, just reading. Encoding equal to utf-8 tf-8. So this is how I read a file as file, if you remember from our first week where we learned how to open files. Now for line in this file, for each line I'm gonna say values equal to line dot split. I'm gonna split them into words, so I'm gonna say word equal to values of 0. Next I'm gonna say coefficients equal to np dot as array, and this I'm gonna pass values of 1 colon, and then data type that I want is of float 32. So that will give me my coefficients, and then finally embedding underscore index of a particular word is equal to coefficients. Okay, that's perfect. So I think I have everything that I need. Embedding index any, okay, I think that's right, but let's see. Print next I'll say f of loaded length of embedding index word vectors. So let's see, embeddings index, that's why it was causing problem. Embeddings in the word vectors. Perfect. So I have loaded my glove embeddings. Next step is to prepare the embedding matrix. So to start with, I'm going to create a variable embedding dimensions equal to, set it to 100. Next I'm going to say embedding underscore matrix equal to, I'm going to create a matrix of zeros, dot zeros, and I'll pass to that our vocab size and our embedding data. Oops, where is my embedding, embedding dim. So once I pass that, next I'm going to go and go through for each word and I in our word index of items. So for each and every word here, I am going to check if I is less than vocab size. So to make sure that it doesn't exceed that, as long as it's less, what I'm going to do is I'm going to say embedding underscore vector variable that I'm creating here is embedding underscore index embeddings index dot get the word. That doesn't sound right, embeddings index, because it's actually embedding index. So I'm going to change that everywhere. So that's good. So that's done. Now next I'm going to check if embedding vector, whatever we got above, is not none. Then I'm going to say embedding matrix of I is equal to embedding vector. So I am embedding, I'm preparing my embedding. This kind of gets me my embedding matrix. Now next step is to build an LSTM model with these glove embeddings. To do that, first let's go ahead and import some things. We need from TensorFlow Keras models. We need the same thing that we used before, sequential. Next I need layers, so I'm going to say Keras dot layers. I need embedding LSTM, and I'm going to use dense. So these three. So now I have these, let's go ahead and here let's define the LSTM model with glove embeddings. So to do that, I'm going to say model equal to sequential. Next I'm going to say embedding is input underscore dim equal to, that was our vocab size. Next our output dim is embedding dim right now, and then weights equal to I will use the, here is where I'm adding the embedding matrix. So I'm going to say embedding matrix, this is new for us. And then finally I'm going to say trainable equal to false. So that's good. Now that I'm done with embedding, the rest of the stuff is pretty much same. LSTM 128 by activation equal to tan h. I'll return sequences equal to false. Make sure the type, there's no typos. Activation, okay, return. Next I'm going to create our final output layer, dense 1 equal to activation equal to sigmoid is what we use, so that's what I'll use. Now once this is done, next step, as we know, is to compile the model. Now to compile the model, I just say model dot compile optimizer equal to Adam. Next I need loss equal to, we use binary underscore cross entropy. Next for metrics I will use accuracy. Next let's go ahead and display this model. So I'm going to say model dot summary. Now once we display this, our next step is to train and evaluate the model. So to train, I'm going to say train the model. Let's say history equal to model dot fit, and to this I'll pass x underscore train, y underscore train. I'll give a validation split of 0.2. I will say epochs equal to 10. I'm feeling very adventurous today. Batch size equal to 64, and I'll say verbose equal to 1. Now this will train the model. Next, go ahead and evaluate it. So I need loss and accuracy. Model dot evaluate x underscore test, y underscore test, and verbose equal to 0. Now let's print the LSTM model with glove test accuracy is accuracy 0.4f. Perfect. So that will give my LSTM accuracy. Now, if you want to compare the performance with the non-embedded LSTM, so I'm going to probably get the code that we wrote earlier to get the get the LSTM without glove embeddings. So I'm going to just paste it here, which is LSTM model sequential embedding input dem vocab size. Output is this LSTM usual and dense. Next we said model.compile. This is what we did. Then we created this. I want to make sure it's as same as this. Validation size of 0.2. Batch size is 32. I'm going to change this batch size to be same 64. And epochs I'll make both of them 5 since I'm running 2 of them. Okay, so I have all the data as same as this. Next, LSTM, evaluate this, and then we can look at the LSTM test accuracy only. So that will give me LSTM test accuracy without glove embedding, and this is with glove embedding. So I'll see both of them next to each other. I am going to cut this and put it here, and this one I'll say accuracy LSTM without glove. Ignore my typos here. I'll try to fix whatever I can. Again, this is glove. So this is what I get. Next, I can also do one more thing to display it. Let's go ahead and import matplotlib, and I am going to plot both of them side by side. To do that, I am going to say models equal to, so what are the two models that I have? LSTM with no embeddings, and the next one is LSTM with glove. So these are my two models. I'm going to say accuracies for these equal to accuracy. One is accuracy, this is LSTM, so LSTM accuracy, and the next one I'm just using accuracy because that was the first one that I wrote. Then I'm going to say plot dot bar models comma accuracies. So I'm going to plot these. I'll say color. I'll give two different colors. For my LSTM, I'll give blue color, and for glove, I'll give green, just to compare. Plot dot title. Now again, these might not be like LSTM might turn out better than glove, but we never know. Comparison of LSTM with and without word embeddings. As I said, these models work based on how much data you give or what type of data you give. So it's always difficult to know unless you use it if it's good or bad or which option is better for you. I'll say plot.show. So I have all that thing that I need. So I'll go ahead and run it. I'm going to save it, open my terminal and say Python day 5 and run it. It's going to take some time, so I'm going to stop here and come back once it completes the entire run. It looks like I have given a wrong word here. Value key for this is a reserved word, so I need to make sure that I don't use, where is that I've used? It did try to tell me that use value, but okay, perfect. Clear it out. Let's see if there's any more errors before we stop this video and pause it for the moment. Okay, it's working, so I'll wait for it to run, and once it's done I will record again. So here we go, and after running for 5 iterations for our data with glove and without glove, this is the output that we see. And as you can see, the accuracy for LSTM is more than 80%, 86%, whereas with glove test accuracy is 53%. So looks like it added more data than it needed then, and kind of made the accuracy much worse as compared to with LSTM. So that might happen sometime depending on your data set. So you have to always try with different combinations to see which model and with what technique it works perfectly fine. So just to summarize, Today we understood the importance of text pre-processing in NLP tasks. We learned the role and benefits of word embeddings like word to vec and glove. We gained practical experience using pre-trained embeddings in deep learning models, and we compared and interpreted the performance of models with and without embeddings. So if you had any problems implementing this or didn't find the files or had any issues or have any questions, just let me know in the messages and I'll get back to you. Day 6, sequence to sequence models and applications. So let's start with sequence to sequence or sec to sec models and their architecture. Now, what are sec to sec models? Sec to sec models map an input sequence to an output sequence of different lengths. Widely used for tasks like language translation, text summarization, speech to text, and chatbots. The architecture involves an encoder which processes the input sequences and encodes it into a fixed length vector, also called as a context vector. Then we have a decoder which takes the context vector as input and generates the output sequence step by step. Let's get into encoder decoder framework for sec to sec tasks. How does it work? The encoder sequentially processes the input sequence using RNN, LSTM, or GRU, and then it produces a context vector representing the entire input sequence. The decoder initializes its hidden state with the encoder's context vector, generates the output sequence one token at a time, and predicts the next token using the previously generated tokens. Next, let's talk about attention mechanism overview. Now, why attention? Standard sec to sec models compress the entire input sequence into a fixed length vector, which can lead to information loss for long sequences. Now, this attention mechanism dynamically focuses on different parts of the input sequence when generating each output token. Now, how does attention work? It calculates a weight or score for each input token based on its relevance to the current decoder state, and then outputs a weighted sum of the encoder outputs, creating a context vector for each decoder step. Let's look at our hands-on exercise for today, where the objective is to build a basic sec-to-sec model using LSTM for translation and experiment with the hyperparameters. So let's get started. Today I'm going to use PyTorch for our project. So I'm going to start with new file and I'm going to save it as day6 underscore exercise. And again, this today we're going to start with PyTorch. So first let's import the libraries. I'm going to say import libraries. First one that we need is import torch. Next we want to import torch.nn as nn. Next I need to import for optimizers optim torch.optim as optim. Next I want to get from torch.utils.data import. We'll get our data loader and we'll get our data set. So we have that. Next, finally, we'll go and import numpy as np because we might need to do some array operations here. Now, for simplicity, we'll use a small manually created English to French translation dataset, and I have that ready. So I'm going to just use that and paste it here. Now, this one has some English sentences like hello, how are you, good morning, thank you, and good night. Now, my French is not good, but based on Google Translate, I got these French sentences. Hello is bonjour, how are you is this, good morning is this, thank you is this, and good night is this. I'm not going to even try to speak French right now. But anyway, so we have this here. Next step is vocabulary and tokenization. That's what we're going to do. Here, I am going to create a function called as build underscore vocab. And for that, I'll pass my sentences. And once I have this, I'm going to create my vocab equal to. In here, we'll add some padding, and so for that, first is pad of 0. Next, we have SOS of 1. Next, we'll add end of EOS, which is 2. Next, I'll add UNK, unknown, as 3. So these are different vocab key value pairs that I have. Now, for sentences that I'm getting in, for actually sentence in sentences that I've been passed, I'm going to run through each and every sentence, and I'm going to say for word in sentence dot split. I'm going to check if word not in vocab, if this word doesn't exist in my vocab, I'm going to say vocab word equal to length of vocab, and then I will return this vocab outside my for loop. So this is my this will create my vocabulary and tokenization. So next step is, let's create the English vocabulary. To do that, I'm going to say build underscore vocab. I'm going to call that, and then to that I'll pass my English sentences here. I'm going to pass it here, and then when I want to create my French vocabulary, equal to build vocab. So this is how translations can be done using AI these days. So you got an idea of where we are heading. So now let's go ahead, and next I want to tokenize and pad the sentences. To do that, I'm going to create a function called as tokenize, and to that I will get my sentences, I will get my vocab, and I will get what is the max length that I want to use here as inputs. Now first I'm going to say tokenized equal to an empty list. So I'm going to initialize with an empty list, and then I'm going to say for sentence in sentences, I'm going to run through each and every sentence, and I'm going to say token equal to vocab dot get word for vocab of, oops, I think I put a little bit extra, UNK, and then for word in sentence dot split. So that will be my tokens. Next I'm going to say tokens equal to vocab SOS, close this, plus tokens plus vocab of EOS. Next I'm going to say tokens plus equal to vocab of, next now padding, pad, close this, times, oops, times max underscore len minus length of tokens. And then finally I'll say tokenized dot append, that's my list here. I'm going to append whatever tokens I created into that. Then finally I'll return my np dot array of tokenized. So I'll pass my tokenized array back to whoever called it, along with the whoever called it with sentences vocab max. I'm going to return back that. Next, what I'm going to do is I'm going to get the max length for English and French. So for that, I'm going to say max length of English equal to max of length of sentence dot split. Now where does this come from? Again, this is something that I'm going to do here for sentence in English sentences plus 2. So that will give me the max length for English. Same thing, I can do it for French. I can say FR max length sentence or split for sentence in French sentences. There you go, plus 2. So that will give me the max length for French sentences. Now when I want to create the database for my English sentences, I'm going to say English data equal to tokenize, and to this I'll pass the sentences first. Then it needs the vocab, so I already created the vocab. I'm pass the English vocab, and the max length I'll pass max length English. Similarly, now I can do, okay, I think there is some problem here. English sentences, not just sentence. Okay, next one for my French data is my tokenize. I pass my French sentences. I'll pass my French vocab. I'll pass my max length of French. Perfect. So this will create, this will have my sample data set created. Now that I have my data set, let's define data set and data loader. So for that, I'm going to create a class called as translation data set. So this is my translation data set, which takes the data set as input. And here I am going to define a initializer first. Initializer which takes self, which take the source data, whichever data it is, either English or French, and my target data. So that's my initializer function. I'm going to say self dot source src data equal to the source data that was passed to me. Next, I'm going to say self dot target data is whatever target data that was passed to me. So that is initialized. So my initial object gets initialized here. Next, I'm going to call the underscore length, and I'll pass self as an object here. And here I will say return whatever the length of self dot source data is. So that will give me the length of the source data. Next, I can say if I want to get a particular item, I'll create a get item function, and to this it needs self and id x and index. So this will return back torch dot tensor self dot src underscore data at that particular index idx. So I'm converting that into a tensor here, and it needs torch dot tensor for self dot target data with that particular index that is passed here. Perfect. So this will return back my target tensor, source tensor and target data tensor back to whoever called it. Now let's go ahead and create those data set elements. So I'm going to say data set equal to call this translation data set, and to this I'm going to pass English data and French data. That's about it. Next, I'm going to create my data loader. Now data loader, I can use the data loader class and pass a data set, something that we've done with data loaders earlier. Comma, I need a batch size of how big batch sizes you want. I'll set the batch size to 2, keep it small enough. And I'll say shuffle equal to true. I don't have that much data, so why not shuffle it? So that kind of creates our data set and data loader. Now the next step is to define the sec to sec model components, which is encoder and decoder. So first, let's create our encoder. Now to create encoder, I will use nn.module in here, and then first the initializer. Initializer, it needs self, and the arguments that it needs, I'm gonna enter it here. Arguments that it needs is input underscore dimensions. I need to pass embed underscore dimensions. I need to pass hidden underscore dimensions and number of layers that it needs, because we are going to use LSTM eventually, that's why. And then here I am going to say super encoder is what the class name, self, and initialize with empty set. Perfect. So that super is called. Next, I'm going to say self dot embedding. If you remember from first few days of this week, this is what we did in for embedding in embedding layer. I'm going to say it passed the input dim and it needs embed dim. So if you want to refresh some of these things, you can just look at some of the earlier day of this week. Self.lstm. For that, I will say I want to create nn.lstm, and to this I will pass this needs embed dim, then it needs our hidden dim, hidden dimension, number of layers. I need batch first equal to true. So this will create our encoder initializer class. Next, we need the forward function. Oops. Forward function, which takes self and x as inputs, and this will create my embedded object, which is self dot embedding, and pass it the value of x. Next, it will create outputs, and it will also create our hidden and cell object. This will be coming from self.lstm and pass it the embedded that we got in the previous step. And then we'll return, we don't care about the output, so we'll just pass hidden and cell back. Perfect. So that's our class for encoder. Now let's go ahead and create the class for decoder. So class decoder, again nn.module. Next step is to create our initializer method init. Oops, I don't know, sometimes I feel like it's easier to handwrite it. Self, we need output dim underscore dim, output dimensions. We need embedding dimensions, embed underscore dim. We need hidden dimensions, same as our encoder, and we need the number of layers that we need. Next, I will call the super class super, and then to this, as before, we will pass decoder and self. Perfect. So that creates a super. Next, I'm going to call the embedding equal to nn dot embedding, and this will embedding needs output dimensions and embed dimensions. Perfect. So once this is done, next thing is our LSTM layer. LSTM needs nn dot LSTM, and I will have to pass the embed dimensions. Next, we need to pass the hidden dimension. Next, we need the number of layers, and next we need batch first equal to true. So this is takes care of ls. Now my fc function is equal to nn dot linear, and then this needs our hidden dimensions and my output dimension. Perfect. So this takes care of that. Next, I'm going to call my forward function, and to this I'll pass self, x, hidden, and cell. So my forward function now will say x equal to x dot unsqueeze first, unsqueeze with 1. So this will add the time dimension. Next, I'm going to say embedded equal to self dot embedding and pass it the value of x. Next, I'm going to say outputs comma hidden comma cell equal to self dot lstm and pass it embedded. This time we need to also pass the hidden and cell, so I'll pass hidden and cell in a tuple. Perfect. So that's passed. Next, let's get our predictions. So predictions, I'll say self dot fc. I'll have to take the outputs from above and squeeze them with the parameter of 1. And now finally I can return my predictions, I can return my hidden, and I can return my cell items back in this decoder class. So I have my decoder class ready. Now finally, let's create our sec to sec class. Now move it up all the way. And I'll start with sec to sec, and I'll pass the nn dot module to it. Now inside here first goes the initializer method. So I'm going to create that init underscore underscore. I am not going to use the autocomplete. Encoder, I need the decoder, and it needs the device. So these are the parameters that we need here inside the initializer for sec to sec. So again, we call the super, pass sec to sec. Next is we'll pass self dot underscore underscore init. There you go, call this function. Perfect. So super is called. Now I'll have to assign the values for encoder equal to whatever was passed as encoder. I'll say decoder equal to whatever was passed as decoder, and finally self dot device is equal to whatever the device that was passed in this particular initializer function. So that will create our basic initializer function. Now let's go and write the forward. This is a little bit complicated because it has a lot of different elements in here. Self, src, target, source, target. Now after target, I'll say teacher forcing ratio. This is used to teach a particular element at 50% is what I'm gonna set. Next, first start with the batch size. Batch size equal to the source dot size at index 0. So that's my batch size. My target length parameter will be, or variable is target dot size at index 1. Next thing is target underscore vocab size. For this, I will set it based on self dot decoder dot fc dot out features. So that's what our target vocab size is. So that should work. Our next step is let's get the outputs. Now outputs in this case is first I have to zero out torch dot by calling torch dot zeros and pass it. It needs batch size as the first parameter. If you see in the help here, it will tell you what all different things you need, but I've done it enough times that I remember. Next, I need the target length. Next, I will need the target underscore vocab size, and that I'll convert dot to self dot device. So there you go. That should take care of the outputs. That will give me the outputs. Next, I need the hidden and cell. That is coming from self dot encoder. If you remember the function that we wrote over there, I pass src to it above. So that will give me hidden and cell. Now next I need is input, and that I can get from tgt target from colon to 0. That will give me my targets. Now let's go ahead and for t in range of 1 to target underscore length, so I'm going to run through this particular range based on the target length. I will get first output comma hidden comma cell by calling the decoder. So I'm going to say self dot decoder, and decoder needs input, it needs hidden, and it needs cell. If you remember, that's what how we created the decoder, which needs all these items, and that's what we'll get output, hidden, and cell from this. Once I get that, I'm going to say outputs colon comma t comma colon. I will assign output to that. So that those are my outputs parameter. Next thing I'm going to do is I'm going to go ahead and why is it moving me? Okay, there you go. Top 1 equal to output. So from my output dot argument max, I'm going to get the first element, and that will be my top 1, which will be used inside the input by saying tgt colon comma t if torch dot random of 1 dot item is less than teacher forcing ratio else, so if it's less than the teacher ratio, which is 0.5, it will set that, or else we'll say top 1 is the value for input. So this we can return back as outputs. We can return back the outputs right here. So next step, after once this is done, let's go and initialize the model and hyperparameters. So I'm going to go outside here to initialize the model. So first let's start with device equal to torch dot device, and to this I will say, now depending on if you what type of system you're running, I'm going to say CUDA if torch dot CUDA dot is CUDA is available, or else we will use CPU. So in my case, probably just use CPU right now. I'm going to say input underscore dim equal to length of English vocab, and for whatever sample we are using here, it will work perfectly on our local computers. Output dim equal to length of, that is our French vocab. Take that, and next we need embed underscore dimension. This I will set it to 64. Next I need the hidden dimension, hidden underscore dim, I'm going to set it to 128, and then I need number of layers, that I'll set to 2. Now these parameters I've set up just so that I can create my encoder, decoder, and sec to sec. So let's call the encoder function or class. This needs all the different parameters that we said. First it needs the input dim, so I'm going to say input dim. Next it needs, as you can see, embed dim, so I'm going to give the embed dim that I've created. Next I need the hidden dim, so I'm going to provide that, and then finally number of layers, which I've also created, so I'll pass those. Next let's create a decoder. Now decoder needs, let's see what it needs. Decoder, it will need the output dim, so we already have that output dim. Next it needs the embed dim, so I'll pass the embed dim. Next it needs the hidden dim, I'll pass hidden dim, and finally number of layers. Oops. Number of layers. Perfect. So that will create my decoder. Now let's create our model, sec to sec. Now this needs, as you can see, encoder, which we just created above, pass that. It needs the decoder, pass that, and it needs device here, which I've mentioned above, depending on what we have, see either CPU or CUDA, depending on its availability, dot to device. So there you go. So that will have my model ready now. Now our next step is to training. So now the model is ready as usual. First let's create our optimizer, that is using optim dot adam, and I'll say model dot parameters. That's the first thing that it needs, and the next thing that we need is the learning rate equal to 0.001. Perfect. So I'm an optimizer. Next criterion for this I will use nn dot cross entropy loss, and I will ignore the ignore index equal to French underscore vocab. The pad part I will ignore that. Padding is ignored here. So that's what I mentioned as my criterion. Now let's create our training function. So I'm going to create a train function. This will need model. We have to use data loader, which we have created already. Optimizer we have set optimizer, so that another we need criterion that is also created above. Next I need device, and I need number of epochs to run this, and this by default I'll set it to 20 because we have a small data set that we've created, so we don't have to worry about that. First let's put it in the training mode, so I'll say model.train, initialize that. Next I'm going to say for epoch in the range of total number of, we're going to run 20 times if not specified. I'll set epoch of loss equal to 0. If you have a bigger data set, you can probably pass that and make it generate better text. Target in data loader. So for the source and target, I'm going to say source comma target equal to src dot to device comma target dot to device. So this will create my source and target. Next, let's create my optimizer. Let's zero out the optimizer. So I'm going to say optimizer dot zero underscore grad. So this will zero out all the previous optimizers. Output equal to model of src comma target. That's what we pass. Next, we set the output equal to output equal to output of colon from 1 to 1 colon dot reshape and pass it -1 to output dot shape of 2. So that take care of our output. Next, target equal to target of colon comma 1 colon dot reshape of -1. So that will take care of my target. Now we need the loss, and then we'll call the backward class, backward function, then step function on the optimizer, and we'll increment the epoch loss. So for loss, I can get it from criterion and pass it output comma target that we just created above. Next, I need to get, as I mentioned, loss dot backward, the backward, and then optimizer dot step up. Perfect. So step. Next, I'll say epoch loss. I have to increment this plus equal to loss dot item. Perfect. This is same as before that we've done. Now let's to check it out. I can always print here f of epoch plus 1, since it starts with 0, divide by total number of epochs, and I'll say loss is epoch underscore loss divide by length of data loader. So this will give us, and then again, if you want to not see the entire numbers, I'll just say 0.4f. So it's only 4 decimal places. Now that it's complete, finally, let's go ahead and train it. Model data loader optimizer is what it needed. Next, optimizer, I have that. I have the criterion, so I'll pass that, and then finally device, of which device I'm running this, pass that. Perfect. So this is done. Our next step is to translate a particular sentence, the actual code to translate whatever is provided to us. We need to go ahead and translate it. For that, I'm going to say define translate underscore sentence. Now, what all does it need? For this, we'll need the model, we'll need the sentence that is passed, we need the English vocab that we've created to check, we need the French vocab if you want to convert to that, I need that, I need the max length in French so that I can see how big, how much far it can go, and then finally device. So this will translate. Now here first I'll say it's pretty much translating is evaluating the model. So we start the model evaluation. I'll get the tokens equal to, now it comes from English vocab, and I'll say get for word that we have English vocab, and then inside that UNK is what I'm looking for. UNK is my parameter that I have for. Now where is the word coming from? Word is coming from in sentence. So our sentence that we have passed, if we just split that, we're taking each word at a time to kind of get the tokens from there. So that will give us the tokens. The next step here is to get the tokens again based on, so first we based on UNK, then but we need to get the start and end. start of statements and end of sentence. So for that, I'm going to say English underscore vocab. My start of sentence is I've used SOS, and my tokens that I got from above plus my English vocab and the end of sentence that I've used, EOS, end of sentence. So that will create my entire token list. Now the token list is created. Let's create the source equal to torch dot tensor, and I'll pass the tokens to it, unsqueeze so it's proper length or proper dimension, dot to device. So that will take care of that. Now let's go ahead and let's go ahead and make sure that we ignore the gradients, so no grade. And this will give us here, let's get the hidden end cell that is coming from model dot encoder, that encoder class that we created, and we pass the source, and that will give us the hidden underscore cell. Oh, I think no underscore torch, sorry, I think when you type too fast you sometimes mess up. No grad, okay, perfect. So I have this. Now next thing, I'll get the target vocab equal to v of k for k, where v in French vocab dot items. I usually try to use better parameters, but it's difficult to do it when you're doing so much coding. Target indices that we are looking for is inside my French vocab, and the ones that I'm looking for is start of sentence in the start to start with. Next, for underscore in range of max, because I don't care about this parameter, I just want to loop through the max length French. That's why I use underscore in here. Now I can say tgt underscore tensor equal to torch dot tensor of tgt underscore indices. There you go, I have that, of indices of -1. That's where my thing is, and then I convert that to device. Perfect. So that will give me my target tensor. Next, I want to get the output hidden and cell. Output hidden and cell. This will come from model dot decoder function that we have written, or decoder object that we've given, and this needs our target tensor, hidden and cell. So this will give me my output hidden and cell. So now I can do my predictions equal to output, and from there I'll get our argument max of 1 dot item. Next I get the prediction. Now I get the target underscore indices. For these I can now go ahead and append the predictions. So now, if also another thing that I have to check here is if predictions equal to French, French underscore vocab of, if it's end of sentence, then what do? I just break out of this. Oops, break again. Forgot to put a colon here. Perfect. So that's done. Now I'm out of it. I've got everything in. Now let's go ahead and get the translated sentence equal to target underscore vocab of I for I in target underscore indices of from 1 to -1. It's all over. And then that will return back. Let's get space and join, and to the end of it let's pass the translated sentence. So that will, is it, I said translate sentence. Okay, translated sentence. Now let's go ahead and test all these things out. So I am going to do a test translation here. Now to do that, first I need a sentence. I'll say sentence is good morning. I'll try good morning and good night. Translation equal to, I'll call the translate function, translate sentence function, pass the model, pass the sentence that we have. It needs English vocabulary that we have created, so I'm going to pass that. Next thing it needs is the French vocabulary that I'll pass. Next it needs the max length for French, so I'm going to pass that because I have that too, max length of French. And then it needs the device, which I also have. So that's why we created all those different things. Now finally, let's go ahead and say translated sentence is, I'll pass the translation object here. Perfect. So this should work right now. I've written a lot of code, almost 169 lines of code to build this entire translation. It's not that too much if you think about it to build a translation engine. But again, my data source is just a list of items here, but you can give data list from somewhere else. If you have some data set available, you can give that as inputs here and it will work perfectly. So I'm going to go ahead and say Python day 6. Let's hope I don't have any typos, which is not possible. Again, this is not closed here, so I'll have to find where is that. I'll have to find SOS. That's what I've used. So let's make sure this is closed. Perfect. So that's good. Let's go ahead if that is the only problem. Nope, we have more issues here. So torch has no attribute ran, which is, where did I give it? So torch.ran. Oh, okay, I see it here. Instead of random, I used ran. So that's perfect. Save, close. Let's clear it out. Let's run it again. And number of epochs is not defined. So let's see, where did I use that number of epochs? That is number of, what was it? Epochs. Okay, there you go. What was the typing? Oh, I missed the H. Perfect. So let's clear it out. Right. If you're following along, you probably have the same errors or you probably already figured out. So there you go. Bon matin for good morning. That's right. And if I say good night, it said bon nuit. So let's go ahead and add that. Clear it out. Run it again. And there you go. We have this working perfectly based on, it tries to train based on the data and gets you as less loss as possible and gives you the translated output from this particular model. Now, just to recap, today we understood the architecture of sec-to-sec models and their use cases. We learned how to implement encoder-decoder frameworks with LSTMs. We gained insight into attention mechanism for enhancing sec-to-sec models and developed skills in building and experimenting with sec-to-sec models for NLP tasks. In our case, we kind of did a translation, built a translation engine. So I hope you were able to follow along and build it. If not, if you were able to get through the code and implement it, that's good. If you had issues or problems or have some questions, let me know in my messages and I'll get back to you. Welcome to day 7 of week 11, our last day of this week. And today we're going to work on an RNN project for sentiment analysis. Now the steps that we're going to take here is first applying RNN, LSTM and GRU models to a complete task, in this case sentiment analysis. For the project overview, we'll choose a task which is sentiment analysis. Another option was text generation, which we kept for later. And inside sentiment analysis, we'll classify text into categories like positive or negative sentiment. Next, we're going to use RNN, LSTM, and GRU models to solve the chosen task. So we're going to use all of them for this particular project. We'll focus on preprocessing, embedding integration, model architecture, and hyperparameter tuning. Next, we're going to look at analyzing the model performance. Some of the key metrics we're going to look for our sentiment analysis project is accuracy, precision, recall, and F1 score. Next, for tuning hyperparameters, we'll look at embedding size, number of hidden units, learning rate and optimizer choice, and sequence length and batch size. Next, for experimenting with architecture and techniques, for architecture variations, we look at single layer versus multi layer RNNs, bidirectional RNNs for improved context capture. For pre-processing techniques, we'll use tokenization, stemming, and lemmatization, and padding for sequence uniformity. So let's get started on our hands-on project for this week, which is build, train, and optimize RNN, LSTM, and GRU models for sentiment analysis. So let's get started. So first, go ahead, create a new file, save it as day 7 project. Inside here, first step is to load and pre-process the dataset. We'll use our favorite IMDb movie review dataset, but if you have any other dataset, go ahead and feel free to use it. Now from TensorFlow dot keras dot datasets, I am going to import IMDb. That's the first step. Next, from TensorFlow dot keras dot preprocessing dot sequence, I will import pad sequences, which we'll use to pad the sequences that we have. So we have both the functions that we need ready. So let's go ahead and load the dataset. Now you're probably used to this. First thing that we have to create is a vocab size, which I want to limit it to 10,000. So that's what I'll specify here. Next, I want to set the max length. We're going to reduce the length here. We can just set 100 for now. Now let's go ahead and load the database. So IMDb dot load underscore data, and here I specify number of words equal to vocab underscore size. Now this will give me x underscore train comma y underscore train as one tuple, and then it will give me x underscore test and y underscore test as a tuple 2. So I have all the data that I need. Now let's go ahead and pad the sequences. To do that, I'm going to say x underscore train equal to pad underscore sequences and pass it x underscore train. We'll pass the max length equal to max length. Next, I need to pass a padding of post, which means pad to the end of the sentence. Next, I'm going to say x test equal to, I'm going to use the same thing. So why not copy paste it? Copy this, paste it here. Perfect. So I have that. Next step is to print the shapes just to check if everything is good. This is where you can actually catch issues. The reason I've done it again and again is a lot of times the shapes don't match, and that's why you get errors. That's probably, if you're one of them, you probably know what I'm talking about. So it's always good to check the shape sizes just to make sure that they are matching, because that's the first place of error that you can get. Dot shape. It's very difficult for me to talk and type, as you can see. Next, I'm going to say test data shape equal to x test and y test dot shape. So once I've cross-referenced this, next step is to build RNN, LSTM, and GRU models. So let's start with RNN. For RNN, as you remember, we probably need something from TensorFlow, dot keras dot models. The model that I'm interested is, which can be used probably all of them, is sequential. Okay, next thing that I need is from TensorFlow dot keras dot layers. For layering my sequential with different layers, I need embedding. I would need simple RNN for RNN and dense. I'm going to import the others when I'm writing the code for them, but this is for RNN, so I'm just stick to RNN. So let's go ahead and define the RNN model. Now to do that, first I'm going to say create a variable RNN model equal to or give my sequential, and then here give my layers. So my layer says first is embedding as usual, and inside embedding I will put input underscore dim equal to vocab size. So this is my input dimensions. Next my output dimensions, output underscore dim equal to the standard 128. So that's all I need to create for embedding. Next I'm going to say simple RNN, and this needs our input 128 and activation. In this particular case I'll use 10H. That's simple as that. Next my final output layer is using dense. I'll say 1 comma activation equal to sigmoid. So again 1 because it's true or false, it's a binary operation, so that's why 1 layer. 1 is the output here as the first parameter. Next let's go ahead and compile the model. Now to compile the model I'll say rnn underscore model dot compile, and I need to pass first is the optimizer, and optimizer that I'll use is the same one that I've been using throughout the week, Adam. Loss equal to, since this is binary operation, I'm going to say binary underscore cross entropy, and the metrics that I'm interested is accuracy. So that will take care of that. Now let's go ahead and display the model summary, how it looks like. Always good to see how it looks up. Summary, perfect. Now I'm going to create all the different models and then we can actually display just for the fun of it. So next thing is LSTM model. So for LSTM, I need to add one more thing here, which is LSTM. That's all I need. The rest of the stuff is there. So I'm going to say define the LSTM model. Say LSTM underscore model equal to sequential, and here I will pass embedding of input underscore dim equal to, it's almost the same as that, so I'm gonna just copy this and paste it. The only thing that changes in here is instead of simple RNN, say LSTM, and I'll pass 128, and activation is also pretty much same, so I could have just kept everything here and just add LSTM in front of it. Now to compile the model, again copy this. To compile the model, I'll say LSTM model dot compile Adam binary cross entropy accuracy, and finally I'll say LSTM model summary. Now the next one is our GRU model. So for that I'll have to go here and add GRU. So GRU is added. Next I am going to copy this, paste it, call this one GRU model, and then I will compile the GRU model with the same parameters, summary, and only thing that changes is GRU here, and it takes 128 activation 10H. Rest of the stuff is exactly same. So this is my, let's say GRU model. Perfect. Now if I want to see all these models before I train and evaluate, because you know how much time it takes for training and evaluation, I just want to see how they look like. So just go ahead and say Python, what is the name of my file? Day7 underscore project py, and look at our models of how they look like. So first it will display me the shape. Right here we have the training data shape and we have the test data shape. Next it shows me the first model, which is simple RNN, and it shows me the model summary here. Next one is our LSTM, which shows LSTM here, and we have GRU here, which shows my GRU summary here. Perfect. So I'm clear this out and let's follow the next step. Next step, as you remember, is to train and evaluate models, which takes forever. So I'm going to start with train RNN model, and for this I'm going to say history underscore RNN equal to RNN dot model, and I'll fit datasets to it. X underscore train, I need Y underscore train, I need the validation validation split, which I'll put it to 20%. Next, I need epochs of how much I want to run. I'll set it to 5. I'll not be too over optimistic for this. I need the batch underscore size equal to 64, and then I will use verbose in deep equal to 1. So that's my RNN model being trained here. Now I can copy the same stuff, go to the end, paste it 3 times. What I'm trying to do is I want to say LSTM and train GRU. Now if you see how they made it so much easier, I can just change it to LST. Oops, I think I have an error here. Perfect, got it early. LSTM model, and my last model is GRU model. So I have made sure that I have using the same training data set, same validation split, epochs are same, batch size is same, and even the verbose is 1. So that's how I train all the 3 models at once, which means I can evaluate all the 3 models together too. So let's go ahead and evaluate models. First one, I'm going to say loss underscore RNN, and what else do we need? Accuracy. Accuracy underscore RNN equal to RNN dot, RNN model dot evaluate, and to this I need to pass x underscore test because I evaluate with test data sets, y test, and then this one I don't need to care about, verbose equal to 0. So same thing 3 times. Now this one is LSTM, this one is LSTM, RNN is LSTM. So now I'm evaluating the LSTM model. Next here, I want to evaluate GRU model. Copy this, paste it here, perfect. So I have my all the 3 models being evaluated. Now let's compare their accuracy one at a time. So I'm going to say print f of RNN test accuracy equal to accuracy RNN, and then I'll use 0.4 f. Now again, why should I type this again? LSTM and GRU, accuracy LSTM and GRU. Now I can run it, but what's the fun in that if we don't display or visualize it in a graph? So I am going to import matplotlib.pyplot. You can just run it if you want to, but again, it takes a lot of time, so it's best to run everything together unless you know that, unless you feel like there might be some error. Plot training, you can always reduce the epochs and run it just to see if it runs properly with just one epoch. Say plt.plot. First I want to use the history RNN dot history. Oops. And inside that I am interested in accuracy, and my label for this is RNN training accuracy. So that's my first, second, and third. Now again, second one, all I have to change is LSTM, and then also give it a label LSTM. Same thing for GRU, and I'll say label equal to GRU. One second, what happened here? History. Oh, I think, see, I have an error here. LSTM, good I saw this, GRU, and then I have LSTM, GRU, all these displayed properly. Okay, next is plot. I want to give a title, sorry, not plot. All my plotting is done. Now I'm going to do training accuracy comparison. Next thing I will say X label. For X label I want to use, as you know, it's epochs, and for Y label I want to use accuracy. And then since we have given label, let's go and display the legend, and finally let's show this. So that's all about it. So let's go ahead and run this project. I'm going to open my terminal and say Python. I think I already gave one, so day7.project. It's going to run initially, and then it will give me the size and the models, and now it's running through the epochs for all three of them. So what I'm going to do is I'm going to pause here and come back once this is complete and go over the output. It took around 5 to 10 minutes, but it was pretty quick this time. And here is our training accuracy comparison, where you can see RNN's accuracy versus LSTM's accuracy, and GRU accuracy is on the top. So this is how you can trace them. Now I'm going to close this here, and you can look at the entire run of the project, where it went through all the first, it showed the summary, then it went through 5 epochs for each, and as you can see, the loss is reducing, accuracy is increasing as and when it goes up. These are the three accuracies that we have. RNN test accuracy is 71%, LSTM is 83%, and GRU is 83% too, but LSTM has a little bit higher here, whereas GRU is a little lower, but on the graph it was showing based on how it is uh, training, and each and every epoch it goes a little bit above. So, and that kind of wraps up our project for week 11, day 7. And the things, just to summarize, we developed skills in pre-processing text data sets for sequence-based tasks. We understood how to build, train, and compare RNN, LSTM, and GRU models, which are very prominent in industry these days. And we learned the challenges and limitations of sequence modeling and how to address them. We gained experience in hyperparameter tuning and also performance evaluation. So I hope these last 11 weeks were pretty good, and we have some interesting stuff coming up next week. So stay tuned.